Okay, so welcome to this next video in which we're discussing tertiary lymphoid organogenesis. So far we've seen that stimulation of the lymphotoxin beta receptor on the surface of the endothelial cells is going to activate a canonical NF-kappa B pathway, which leads to the activation of this P65-P50 dimer form of NF-kappa B, which is going to increase the expression of proteins involved in type 2 activation of endothelial cells. So this canonical pathway is not terribly involved in the conversion of the endothelial cells of the postcapillary venules into high endothelial cells. However, it is a pathway which is involved in lymphotoxin beta receptor, and therefore I feel that we need to discuss it in order for our discussion to be complete. Okay, so we've seen one of the proteins that's going to be upregulated, which is COX-2, which is going to increase the synthesis of prostacyclin by the endothelial cells. And you might think, well, why on earth do endothelial cells in venules need to be producing prostacyclin? They have no smooth muscle cells around them. But of course, what you have to realize is that if we draw a venule here, so if this is a venule, then you'll also have arterioles nearby. So maybe this blood vessel over here is a little arteriole. Okay, so this arteriole might not necessarily be the arteriole that connects up to this venule, but it's another arteriole in the same sort of region as the venule, which I'll show in blue here. So if the endothelial cells of this venule are producing prostacyclin, then it will be being released into the interstitial space, and it may well be able to diffuse over and find arterioles, which are also supplying the same area. Even if this arteriole doesn't directly connect up to this venule, it's still in the same area. Okay, so the prostacyclin produced by this venule can go over and act on the arteriole over here and cause vasodilatation of that arteriole by relaxing the vascular smooth muscle cells, okay, which will increase blood flow to the area. In addition, what type 2 activation is going to cause is it's going to cause an increase in transcription and then translation of proteins which are not currently identified, but we know they must exist and because we know what they do. So let me explain what they're going to do. So let's get another piece of paper. Okay, so it's going to cause the expression of proteins which are involved in retracting the actin and tubulin cytoskeletons. Let me explain what I mean by this. So basically, if you want to increase vascular permeability, which is part of the inflammatory response, then one way to do it is merely to pull the edge of the endothelial cell backwards a little bit. Okay, that's what happens in type 1 activation. You get a process known as endothelial contraction, which basically pulls the proteins that are involved in the tight junctions and the adherens junctions between two neighbouring endothelial cells. It pulls them apart to destroy the tight and adherens junctions and then create a little gap between the two endothelial cells. However, a more permanent way to do it is to actually dismantle the actin and tubulin cytoskeleton at the edges of these endothelial cells. Okay, so let me explain something. So basically, if you want to understand the purpose of the cytoskeleton, then you need to remember that cells have a set shape, but what is actually holding them in that shape? Often when we draw a cell, we just sort of draw a circle like this to represent the cell membrane, maybe and put a nucleus in there. And we draw the cytoplasm as though it's empty, but the reality is the cell membrane is not what keeps the cell in its set shape. Instead, there is a meshwork inside the cell which is keeping it the same shape. Okay, remember the cell membrane is just a mush basically. It would collapse easily without something that's holding it up. So inside the cell, in the cytoplasm of the cell, you have a cytoskeletal network, okay, made up of a huge number of protein filaments. So if we were to actually draw it, it would look like something like this. Protein filaments everywhere, all intertwining, all joined together, forming a very rigid structure within the cell, okay? And this is what holds the cell in its fixed shape. Okay, so what are these filaments? What are these cytoskeletal filaments which determine the shape of the cell? Well, basically, they are polymers of small proteins, and the two small proteins that you can polymerize to make large polymers, which are going to be the main component of these cytoskeletal filaments, are actin and tubulin. Okay, so the cytoskeleton is mainly made up of actin filaments and tubulin filaments. Now, if we were to dismantle the cytoskeleton in the edge of this endothelial cell, so for instance, if we were to dismantle the actin and tubulin microfilaments in this portion here, which I'm now highlighting in turquoise, what would happen to the endothelial cell? Well, basically, if you dismantle the cytoskeleton, then there's nothing holding the cell membrane in this shape anymore, and basically it will just flop back. So it'll flop down. So you can retract the whole edge of the cell by dismantling the actin and tubulin filaments. And you can do the same in this endothelial cell here. You can dismantle the actin and tubulin filaments in the edge of this endothelial cell, and that will cause the retraction of the edge of the endothelial cell. So the boundaries of these endothelial cells will move backwards, basically, and this will create a gap between the two endothelial cells. And in type 2 activation, NF-kappa B is going to increase the expression of proteins which lead to the dismantling of the actin and tubulin cytoskeleton right at the edges of the endothelial cells, so that you get the retraction of the edges of the endothelial cells and the opening of a gap between the neighboring endothelial cells. Okay, so the proteins which do this, as I say, are not known. They're unknown effector proteins. That's the nice terminology people use for it. So we will know them soon, presumably, but at the moment we don't know what they are. Okay, and what's the overall point of this? Well, the point of this is that now you've got a gap between the two endothelial cells, and fluid can move from the blood through this gap into the interstitial space. So this is going to help increase vascular permeability, and therefore help in the formation of an inflammatory exudate, which brings the complement proteins and the coagulation factors in, which are going to help deal with our infection. Okay, so that's one of the things that's going to happen in these endothelial cells in response to lymphotoxin beta. Okay, now you might think, oh gosh, didn't this happen ages ago in response to interleukin-1 and tumour necrosis factor alpha? And I would say, yes, you're right, it did, but these lymphocytes are helping to maintain this type 2 activation throughout the chronic inflammatory period, basically. So it's a way of maintaining the type 2 activation for as long as the inflammation continues. Okay, so here's another aspect of the type 2 activation. Okay, so what's the next aspect? Well, the next aspect involves the recruitment of leukocytes from the blood. So, if we've got an endothelial cell here, then in response to the NF-kappa B becoming activated, what will happen is you're going to express two proteins which are going to help you recruit neutrophils from the blood. Okay, and these two proteins are E-cadherin and CXCL8. Okay, so one of them, where should I draw this one? I'll put it here. So you're going to put on your surface a protein known as E, and it's not E-cadherin, sorry, E-selectin is what I mean, not E-cadherin. E-cadherin is something that cells use to join together, so it's similar, but E-selectin is what you're going to put on your surface. Okay, so here is E-selectin in purple. Okay, and you're also going to put CXCL8. So let me discuss what CXCL means. Okay, so CXCL8 is also known as interleukin 8. Okay, and CXCL8 stands for CXC chemokine, which is a whole family of chemokines. And then this is CXC chemokine ligand 8. Okay, right. So, basically, the CXCL8 is going to bind to polysaccharides which are on the surface of the endothelial cell. So on the surface of the endothelial cell, you have heparan sulfate proteoglycans, which are massive, great polysaccharides which are attached to proteins in the cell membrane. So this green stuff that I put on the surface of the endothelial cell, this is heparan sulfate. Okay, now you have more polysaccharides than just heparan sulfate on the surface of your endothelial cell, and this polysaccharide there that's on the surface of your endothelial cells, this has a special name. It's known as the glycocalyx. Okay, so it's over all endothelial cells within the bloodstream, and it's really more something like a slime, basically, that lines the endothelial cells. Now, basically, one of the components of this glycocalyx is heparan sulfate, and this CXCL8, this CXC chemokine ligand 8, is going to get attached to the heparan sulfate within the glycocalyx. Okay, so this here, this is CXCL8. Okay, so I'll highlight that in blue. Now, these two proteins, E-selectin and CXCL8, are going to be expressed on the surface of endothelial cells in response to NF-kappa B. So NF-kappa B is going to increase the expression of E-selectin and CXCL8 on the surface of the endothelial cells. Okay, now, this is going to help with the recruitment of neutrophils into the site of infection, basically. So here is a neutrophil with its multi-lobed nucleus here, okay, and the archetypal number of lobes for a neutrophil's nucleus to have is 3, so we'll draw 3, and it has receptors for both of these. So it has a receptor for, well, it doesn't have a receptor, it has a molecule, a ligand for E-selectin, okay, and this is sialyl Lewis X. So this isn't a protein, it's a little carbohydrate, sugar molecule, okay, so this is sialyl Lewis X, which is on the surface of the endothelial cell, on the surface of the neutrophil, and will bind to the E-selectin on the surface of the endothelial cell. So I will colour in sialyl Lewis X in turquoise here. Okay, and the neutrophil will also have a ligand for CXCL8, and this is a receptor. So it will have some form of CXC chemokine receptor on its surface that binds to CXCL8. Okay, so we'll put the CXC chemokine receptor, which is abbreviated to CXCR, in red there. Okay, now this allows the neutrophil to bind to the surface of the endothelial cell. Now, the bond between E-selectin and its ligand, sialyl Lewis X, is quite weak, and it's known as the tethering of the neutrophil to the endothelial cell. So this bond is called tethering. Whereas the bond between the CXC chemokine ligand 8 and the CXC chemokine receptor is far stronger, and that's known as the tight adhesion between the endothelial cells, between the endothelial cell and the neutrophil, rather. Okay, and now what will happen is the neutrophil will diapodese across the endothelial layer between the endothelial cells. So what will follow is a process known as diapodesis. So let me show this. Okay, so here is our endothelial cell. Okay, and here is our neighbouring endothelial cell over here. Remember, they've opened up gaps between them, but that gap still isn't big enough for a cell to fit through, at least not without help. So So once the cell, this neutrophil, has bound to the surface of the endothelial cell, what will follow is this process of diapedesis, where basically the cell deforms itself so that it can sliver through the gap between the two endothelial cells. And this process of squeezing through the gap between the two endothelial cells is known as diapedesis, and it's how you extravasate all leukocytes. Okay, so the activation of the expression of E-selectin and CXCL chemokine ligand 8 is going to lead to the recruitment of neutrophils from the blood into the interstitial fluid. In addition, what it's going to cause is the recruitment of monocytes, because as well as leading to the expression of E-selectin and CXCL8, NF-kappa B is also going to upregulate the expression of molecules involved in the recruitment of monocytes. Okay, so let's talk about this. So here is our endothelial cell. Okay, and basically the NF-kappa B is going to increase the expression of two molecules on the surface here, two proteins, known as ICAM1 and VCAM1. And it's also going to upregulate a chemokine, which again, just like CXCL8, will bind to the heparan sulfate within the glycocalyx. So here is the glycocalyx. And basically, again, you're going to upregulate a chemokine that will bind here. Okay, so this chemokine this time is a CC chemokine by the name of CCL2. Okay, which stands for CC chemokine, which is again a huge, great family of chemokines. And this is CC chemokine ligand 2. Okay, CCL2 for short. So let's colour in CCL2 in blue here. Okay, and then these other two proteins here, they represent ICAM1, which means intercellular adhesion molecule 1. So this is ICAM1, okay, which stands, as I say, for intercellular adhesion molecule 1. And this is the exception to the rule of CAM. Well, it's only a minor exception. CAM usually just means cell adhesion molecule, but this time it means intercellular adhesion molecule, so a slight difference. Okay, intercellular adhesion molecule 1. Okay, and then this other molecule is going to represent VCAM1, which stands for vascular cell adhesion molecule 1. Okay, so the endothelial cell will express both of these on its surface. Not vascular endothelial, I'm thinking of vascular endothelial growth factor. Vascular cell adhesion molecule 1. Okay, and both of these are going to help with the recruitment of monocytes from the bloodstream. Okay, so here will come our monocyte, and monocytes have a single nucleus, so they have a large, big nucleus here. And basically it will have ligands for these molecules that we've put on the surface of the endothelial cell. So the ligand for ICAM1 is a protein known as LFA1. Okay. The ligand for VCAM1 is a protein known as VLA4. Okay, so this is VLA4, standing for very late antigen 4. Okay, so this stands for very late antigen 4. And then finally, you'll also have a receptor for this CC chemokine ligand 2, which will be a CC chemokine receptor, so a CCR of some description. Right, so let's colour everything in. So we'll have the CCR in red here. Okay, we'll have ICAM1 not in green, because it will get confused for the glycocalyx then. We'll have it in turquoise. Okay, we'll have VCAM1 in orange. Okay, and we'll then have LFA1, or LIFA1 as it's often spoken as, in pink, and we'll have very late antigen 4, VLA4, in yellow. Right, so this is how you're going to get monocytes sticking to the endothelium. These monocytes are then going to diapodese between the endothelial cells into the interstitial space, and when they get into the interstitium, they're going to differentiate into macrophages, and they're then going to phagocytose the microbe. So, this is how lymphotoxin beta is stimulating type 2 activation in endothelial cells, okay, which is maintaining the inflammatory response in this chronically inflamed tissue. Okay, now what we'll look at is how it also triggers the non-canonical NF-kappa B pathway, which is actually going to lead to this transformation in the endothelial cells in the post-capillary venules, which will lead them to become high endothelial cells, and how that's going to help with the recruitment of naive T cells, naive B cells, and therefore the production of this tertiary lymphoid organ.